My name is Jonathan Larson, and I'm a physics postdoctoral scholar at Lawrence Berkeley National Laboratory, where I work in the Energy Storage and Distributed Resources Division, and I'm a member of the Kostetsky Group. In addition to this, I'm also an affiliate of the IR group at the ALS. Thanks so much for taking the time to listen to my talk. Today I'm going to be speaking with you about Nano-FTIR of buried electrochemical energy storage interfaces and interphases. And starting right off the bat, I'd like to just splash up a quick schematic here of an anode-electrolyte interface that would be common in a lithium-ion battery. And what happens upon adjoining these two materials and then with subsequent electrochemical processes is that there is a growth of an interphase that is both chemically distinct and structurally unique, and is actually very critical to battery function and operation. Across this interphase will shuttle lithium ions, but it will restrict the flow of electrons that would cause continued degradation of the electrochemical cell. Because of the absolute kind of central importance to the interphase, as new chemistries and technologies are proposed, there's kind of an increasing need to be able to characterize these interphases and kind of glean a better basic understanding of how they really function. Because, like I say, they're totally critical to the battery success. And over the years, our kind of state-of-the-art understanding of these interphases has changed dramatically. And this is because, in large part, these interfaces are dynamic, they're chemically heterogeneous, they're nano-thin, they're very reactive. In a nutshell, they're hard to study, and especially in situ and especially non-destructively. And so we see in our group that there's at least three major needs to kind of advancing new novel methodologies. And they are the need for nanoscale resolution, the need for non-destructive characterization, and the need for characterization of these interphases within their native environment. And I've just listed here on the right our solutions for these: AFM, Nano-FTIR, for the nanoscale, for the non-destructive component, tapping mode and the low energies afforded by infrared light. And then finally, how we access the native environment is through multifunctional graphene membranes, as described in the following. So it is very common to attempt to characterize interphases from the electrolyte side, but this comes with a whole host of challenges. And so we have pioneered new approaches with our collaborators to investigate these interphases from the side of the working electrode. And this is done by making the working electrode nano-thin and infrared transparent, and thereby enabling us to characterize the interphase within its native environment and eliminating all those other challenges previously mentioned. And the material that we use for this is monolayer graphene. So splashed up here are kind of like two TOC-type images of two of the recent publications, of which I am co-first author on each, that utilize this approach of graphene membranes, which function as both infrared transparent window and model working electrode. And the first one that I'd like to discuss with you is the one based on liquid electrolytes. So this work came out in 2019 in Nano Letters, and in the top left is a schematic of the liquid cell that was used to accomplish this work. And in the bottom left is a schematic of one of the holes in the perforated silicon nitride membrane. And to start the work and to demonstrate that we could take Nano-FTIR spectrum of the liquid environments through the backside of the graphene, we first tested this with water, which is displayed in the top middle, and compared to the ATR-FTIR measurement of water, and then as well as anhydrous propylene carbonate, which is bottom middle. And so those were very, very nice and exciting spectra. But then what was really cool was we moved to a salt-rich solution, basic salt-rich solution, but one that would afford us the opportunity to investigate an interphase or a region at the interface that was different from the bulk. So if some of you have read kind of introductory electrochemistry textbooks, when there's a salt in the solution, the interfacial region will have, a double layer and a diffuse layer. And those kind of interfacial regions will also be sensitive to bias that's applied. And so what we found first and foremost was that when we took Nano-FTIR of a graphene interfaced with 0.1 molar ammonium sulfate and water, we found that there was unique interface-specific species that were present that were not ever recorded in the ATR-FTIR. Only the Nano-FTIR had them. And then excitingly, when we applied biases to these, they'd actually change in relative intensity, just kind of like what's predicted in the electrochemistry textbooks. So this was a really good accomplishment for our group, we felt, and kind of was utilized as a springboard to move on to other things. But kind of the big conclusions were that the measurement of liquids in liquid environments with broadband Nano-FTIR was possible, and especially that we were sensitive to interfacial chemistries. And those three ends that I referenced earlier were accomplished, that we were able to look at this interface with nanoscale sensitivity in a non-destructive fashion and within their native environment. And so the most recent work that came out here in Nature Communications, I believe in March of this year, is what I'd like to talk about next. And this was a solid polymer-electrolyte that was utilized. And also, furthermore, the device had a proper kind of counter and reference electrode in actually having lithium foil. And so what we did in this case is we collected Nano-FTIR and ATR at 4 electrochemical states of the device, in the pristine state, in the heated state, and then after plating, and then after stripping. And so down at the bottom here are cross-sectional illustrations of what the interfacial region may look like based upon the data we collected. But ultimately, as I hope I'll be able to convince you of, we were able to glean from the Nano-FTIR data important physiochemical information that we could correlate to the processes that end up resulting in inhomogeneous SEI formation and electrolyte decomposition. Oh, and I'll just mention before I go to the next slide that the chemistry, stoichiometry of the solid-state electrolyte here is PeO10 LiTFSI. So in the left column, you see Nano-FTIR absorption data of the pristine interface, and then in the center column, spatially dependent Nano-FTIR data after heating, and they're color-coded to match where they're collected. And while I don't have enough time to kind of justify each one of these points, you can certainly look to the Nature Communications paper for more details. What we found is that the intrinsic solid polymer electrolyte interface has variations in salt concentration, in PeO orientation, and TFSI orientation and configurations. And this is all on a spatial scale of about 100 nanometer separations. And that after heating, while these heterogeneities decrease, they don't vanish altogether. They still persist to some extent, which is made kind of visible by the kind of the width of this error bar band here in pink. And so this is actually relevant for subsequent electrochemical processes, because intrinsic to this common solid polymer electrolyte are nanoscale heterogeneities, which will give rise to heterogeneities in lithium-ion conductivity, because it's known that some of these physicochemical properties, such as the salt concentration, are directly correlated with lithium-ion conductivity. And when we look at the interface post-plating, that's precisely what we find. We find a heterogeneous both in structure and in white light imaging. You can see that there's a lot of contrast in the white light image, which we attribute to nanoscale heterogeneities in lithium plating. And this is further supported by actually heterogeneities within suppressed absorption features. So let me draw your attention to just two traces, the blue and the green. These two correspond to 0.3, which has a lot of white light response, and the green, which has very little white light response. And so just think in the limit of infinite lithium, right, you're not going to have any DC absorption signals. They're all going to be screened out, right? But if you have no or little lithium, then the DC signal probably won't be screened out as much. Or by DC, I'm saying like the lower frequencies. And so that's exactly what we find. And actually, there was a linear correlation between those that you can see in the paper. And it's also seen in the Nano-FTIR reflection. But the point is that we were able to quantitatively connect that the intrinsic heterogeneities within the solid polymer electrolyte at roughly 100 nanometer separations kind of gives rise to this inhomogeneous lithium plating on a similar spatial scale. Another finding was that of the emergence of new vibrational modes. This is just an example here for C double bond O, but what this tells us is that an SEI is forming in an inhomogeneous way, and or that there is inhomogeneous electrolyte decomposition. Another really important finding of looking at this data is actually the absence of peaks that indicate PEO as crystalline. Now, I didn't show this data earlier, but in the pristine and the heated cases, there are two very clear peaks between 800 and 1,000 that exist. And if you look at the ATR for this exact same interface, okay, so for the after plating case, those two peaks still exist. So what does this tell us? There's a discrepancy in the spectra between Nano-FTIR and the ATR. So what this is telling us is that the bulk is still in its semi-crystalline state. Okay, there's still a good bit of the PEO that's crystalline. But at the interface, within the interfacial region, that the plating process has caused PEO therein to become amorphous. So there's been a phase transformation there. And this is important for lithium-ion kinetics because it's also well known that lithium ions more readily transport through amorphous PEO than they do crystalline PEO, which is an interesting finding that this naturally arises. Okay, so let's turn now to the final state, which is the stripped state. So this is after we've stripped the lithium away, and we should be left with just the SEI. And so we see now an interface that looks completely different from the original pictures that we were looking, at the large high aspect ratio nanoscale grains. Now we have kind of more micro or mesoscale large grains, and we found that there was two almost types of SEI, which are supposed to be represented by the orange and the green absorption spectra and correlated dots. And I might just note that we also find that that structure isn't necessarily correlated with chemistry here, which is an interesting finding. So for instance, here, this is associated more with like SEI region 1, and 5 here is associated more with SEI region 2. And some of the differences in the chemistry and whatnot, and some of the similarities are concisely shown here in this Venn diagram. And again, I'd encourage those of you who are interested to take a look at the Nature Communications paper, because of course that's where all the details will be. So we found that nanoscale heterogeneities implicit to the interfacial solid polymer electrolyte are likely the origin of non-uniform plating and stripping, electrolyte decomposition, and SEI formation, and that molecular level engineering is needed to overcome these challenges if solid polymer batteries are to be commercially viable in the future. And some key general conclusions were that a methodology was developed that can characterize electrochemically active buried interphases and interphases within their undisturbed native environments, and it is amenable to a whole host of other chemistries and battery storage strategies. And so we hope to use this technique a lot more in the future. And so with that, I'd like to say thanks to my collaborators and funding sources and for your attention. Thank you very much.